Okay, welcome to the talk about GSM and how to intercept GSM traffic. This talk is split into two sections. It's me, Steve, and there's David as well. So I'll talk for 30 minutes about GSM and GSM security, tell you a little bit about the security problems that there are, and then David will explain you how you can crack A51, and yeah, we'll have some fun with that. So first, let me explain a little bit about us. We started this project about a year ago in January 2007, and we wanted to receive GSM traffic, and we did this because no one else has done this, and we thought it's quite interesting to get into. So it's like a non-commercial project, and it's just fun basically what we do. Now, today we start directly with the GSM network. I'll explain you a little bit how it works and about GSM in general. So GSM is a specification for a digital mobile network. GSM was designed in the 80s, and the first GSM call was made in 91, I believe. And currently GSM has 2 billion subscribers. It's the largest mobile network in the world. That's 2 billion subscribers, okay? That's pretty large. There are more phones in the world than computers, just to give you an idea how big this world is. Now, when we take a look at the GSM network, we have different computers. We have like the mobile phone on the left, and then we have a base station with a base station concentrator, a lot of other switches and stuff like this. But we'll focus today on the AUC, which is our authentication database, and on the radio link between the mobile phone and the BTS. You have to imagine for people who still think phones are just phones, this phone that I'm holding here is like a standard Nokia phone that you can buy in a shop, but there's a lot of computer power in there on very dense space. Okay, so these are very, very powerful devices. And in fact, this phone is access to a big network of 2 billion subscribers. This is like a network plug, and you can reach anyone in the world, any of these 2 billion hosts, anywhere. The addressing is not IP, the addressing is just by telephone numbers or by other different kinds of addressing. So this is like a network plug to a network that hasn't been discovered a lot, and no one really played around with it a lot. Now let's take a look how GSM works. Let me go back one slide. There's a mobile phone, and the mobile phone talks via radio to a base station. And the base station looks like this. I'm sure you've seen them when you drive around on the highway. You see these antennas sticking out of the forest. And on top of that, you see 3 antennas, each is broadcasting into separate direction, 120-degree angle. And sometimes you don't really see them. Sometimes they're hiding them. So there's a base station here in a tree because people started to complain that of all the metal base stations in the front yard. So they start to hide them in the trees as well. Now let's get a little bit more details about GSM. When you talk about GSM and how GSM works, first off, we have to know that it's a radio protocol, and the mobile phone receives and sends on 2 different frequencies. And these frequencies can be received with hardware that you can buy on the internet. So let's have a quick summary of GSM. GSM is very old, from the 80s. GSM is very big, 2 billion subscribers, and there are different standards. There's 3G, UMTS, Edge, WCDMA, and there are base stations all over the world and all over the place. Now, when we started to receive traffic, we had a couple of choices of hardware devices that we can use. One of the devices that we used was the Nokia mobile phone. What's special about this Nokia phone is it's a standard phone, very old phone. It costs like $1 on eBay. And this phone was shipped with trace functionality and debug symbols enabled by mistake by the manufacturer. So you can connect this mobile phone to your computer, and you can actually listen to what is happening around you, what other mobile phones are doing around you. You can listen on the beacon channel, on the broadcast channel. And we wrote a software front end to this, so that it decodes all the GSM message up to layer 3, I think, up to SMS stuff. Other devices that are out there are devices from Ericsson. You can use Ericsson phones, but also Texas Instruments, who is a major manufacturer of digital basebands. They are soon releasing a development board where you can develop your own GSM stack, and you can play around with this. And my favorite device is a USRP. which is a universal receiver, which basically can receive anything from 0 to 3 gigahertz, any kind of frequency, depending where you tune it into. And it's cost around $700. It's an open source project, so there's new radio around, and all the software is all public. There are people who use the USRP to receive normal radio. People wrote front ends to receive TV with it. Some others did GPS receivers, and no one has done GSM, so we thought, let's do GSM. Okay, now what I'm going to show you is one of these Nokia traces. So I connected the Nokia phone to my laptop, and I received a trace. I started the trace modus to receive traffic. I wanted to see what's happening in my area, which phones are there, and what are they up to. So this is one of the example traces, the output of the program that we wrote to decoding the messages. And you see, for example, here that there's the IMSI broadcasted in clear text over the network. This is something that shouldn't happen, because when you read the GSM specification, it says the IMSI shouldn't be, this is the International Mobile Subscription Identification. It's a unique private identifier for every person on the network. And it says in the standard it shouldn't really be broadcasted over the network in clear text. But this was pretty much one of the first traces that we did, and we gathered within 10 minutes over 1,000 IMSIs. So they're out there quite a bit. Yes, please. This is on your SIM card. Yeah, this is a unique identifier which is on your SIM card, which only you should have access to. There's something else which is called the EMI, which is the International Mobile Equipment Identification, which identifies uniquely your device itself. And it also gives you back the version of the phone. And also this is broadcasted in clear text, yeah? So both IDs are broadcasted in clear text. With equipment identification, you could, for example, know what type of phone they're having. Is it a Nokia phone or an Ericsson phone, and which firmware version is running on them. That's all encoded in the EMI. There are other information that are broadcast in clear text over the network. For example, information how far your mobile phone is away from the base station. So when I turned on this trace, I instantly could see 10 other mobile phones and knew how far they are away from the base stations. And this is pretty precise, up to 200 meters precise. So you can track people even with a $1 device. Now, a little bit more about GSM technology, how this stuff works. I mentioned earlier the radio signal is received over on different bands, and there's 2 different bands used for sending and receiving, which makes it easier for us, because if we only want to receive, we just tune our USRP to one specific frequency, and we just record all the traffic on that band. A burst, it's all separated in bursts, and a burst is roughly 156 bit. Which is 0.577 milliseconds, and in this 156 bits, there are 114 bits user content data that you can actually use. Now let's see another example. This is now the example sent back from the base station to the mobile phone. With the trace mobile also get this kind of information. The mobile station announces here to the mobile phone what kind of encryption is available. So we see A51, which is a stronger encryption, is available. A53 is not used at all. And A52, also the weak encryption, is available on the mobile base station. What is encrypted on a network is voice data, but also text messages and SMS are encrypted. In most specification, in the specification it says it's up to the mobile operator to encrypt SMSs, but in practice when we checked, they were encrypted everywhere. But we'll explain you later how we crack the A51, because ultimately that's our goal. Okay, summary receiving. We know it's cheap. The cheapest device is $1. Shipping probably is 10, but that's how it goes. We know it's very easy. And we know it's getting easier. Let's talk about security of GSM. Where do we have security? Now, when you take a look at this entire network, the only security you have is there. Okay, let me do this again. This is the entire network. This is where you have security. Network, security. Network. Okay, and this security on the radio link, it was broken. It was broken already 10 years ago. In 1998, Shamir and other researchers came up with the results and says, we have reversed the algorithm and it doesn't look very good, and here's a theoretical paper how you can crack A51. But it was not really practical. You still required a lot of data, you required 2 minutes of known plain text, and you need a very clean signal to do this. So it was all theory. Then in 2003 we saw the first commercial equipment appearing on the internet. And in the commercial world, that enables you to 100% passively crack A51. And I go into this a little bit later. Yeah, here we go. So there's a difference between active equipment and passive equipment if you want to intercept GSM signals. An active system basically simulates a base station. And it says, you know, I'm the strongest signal in the room, and the mobile phone is stupid enough to just always pick the strongest signal. It doesn't matter if it's done by a hostile base station or friendly base station. And this base station would then say, yeah, you know what, but I don't support any encryption. So the mobile phone will happily log in and without encryption. So the person can decrypt this stuff. Or it would downgrade to A52, which can be easily cracked. And these devices can be ordered over the internet, and they cost around 70,000 to 500,000 US dollar, depending on how many channels you want to intercept and how nice a user interface should look like. And yeah, 2003 was the first time passive equipment appeared, and these are 100% passive systems, so they do not interfere anymore with the GSM network. They do not transmit any data. They're completely passively sniffing and recording the data and then cracking it. Now, the big advantage of this is that GSM signal, the mobile phone, transfer over quite a far distance, up to 20 miles. So if you're sitting here, you can probably pick up conversations that are happening in the White House even further away. It's 20 miles radius. Now let's talk a little bit more about radio security. The different algorithms, the A51 is the strongest, but that has been broken in theory in '98, and David is later presenting the idea how you can crack this much cheaper. You saw a version for $1 million US, but we just didn't have the money, so we made it for $1,000 US. Well, what else is wrong in radio security? Well, the algorithms are proprietary. Most of the algorithms are not known. The GSM Association is still not giving out some of the security algorithms that they're using. For example, the COMP 120 version 3. They keep this very secret. Why they keep this secret, I don't know. But if I would do good cryptography, I would be proud of what I'm doing, and I wouldn't have any problem sharing it. Now, we have seen that the IMSI location information and your equipment identification is all sending clear text all over the network. We have seen that, that the keys are artificially weakened. That's what they found out in 99 as well, is when you take a look at the SIM card, and the key should be 64 bits, they found out that 10 of the last bits were artificially set to 0. So they approached the mobile operator and asked them, hey, mobile operator, why do you set my last 10 bits to 0? And the mobile operator said, nothing. Now, let's go to the next thing. We also know that the keys are reused. Now, session keys should never be reused. For every session, for every phone call that you're doing, you should negotiate a new session key. In GSM, that's not the case. Your same key is reused for up to 16 phone calls. Not a good thing. There's no indication to the user. Earlier phones, you could see with a little lock on your call that you are now using strong encryption. Well, strong here means A51. But the mobile operator and the manufacturers removed this sign. And only recently now there are a couple of phones that actually show this. Majority of these phones don't give you any indication if you're on an encrypted base station or non-encrypted base station. And it's totally up to the mobile operator to enable or disable encryption. Yes, and I've shown you that there are key recovery systems available for $1 million US. Now, other scary things out there. There's something called the SIM toolkit. And I mentioned earlier that the mobile phone is a very powerful computer. But in your mobile phone, you also have a SIM card. And the SIM card is powerful as well. In fact, on the SIM card, there is a Java virtual machine running on there, and there's a complete operating system running on there. This operating system is always running whenever you have a mobile phone on. And the mobile operator has the ability to remotely install binary applications onto your SIM card and execute these binary applications. The mobile operator can also do this without you notifying. When you read through the standards, you read, if you set this flag, then it is invisible, and the subscriber's he's not aware that you update his mobile phone. So yeah, just reading the specification sometimes is really fun. They call it the OTA. It's over-the-air update protocol. And for example, there's a specification that says what kind of application you can write and what capabilities you have, how the API looks like. And there's one API, what they call Call Control API. And the API lets you control the mobile phone from the SIM card. So you have access to GPS, you can initiate a call, you can send an SMS and receive SMSs just from an application running on your SIM card. And again, this application can be remotely installed onto your SIM. This call control can also tell the mobile phone itself that whenever you do a phone call, the mobile phone first informs the SIM card that the phone call is made, then the SIM card and your application has the ability to modify this call control and then initiate a call. So let's think about this. If I write an application and install it on a SIM card, I'm being informed when the user wants to initiate a phone call. I then, instead of initiating the phone call, I initiate a conference call to the original caller that the user wants to call and to the guy who wants to listen to the traffic. So this is an easy way how you can listen to someone and how you have scary Java applications running on your SIM card. Now, how is this secured? How is the SIM toolkit secured? Yes, there are keys. Yes, there's DES being used, but also 3DES is being used. 3DES, I'm quite happy with that. With DES, I'm not. But when you read the specification, there's also an authentication algorithm that they say this authentication algorithm is implicitly known to both operators, to the mobile phones, to the manufacturer and the mobile operator, and they don't give you any clues what they have implemented there. And usually this means, yeah, not good things, XOR or something. So I wouldn't trust this a lot. Now, the entire development kit, if you want to develop your own Java programs, is available from our webpage, but also from GEM+ website. It's all public, and there's not a big secret in there. So, summary security, there's none. Okay? When you think about it, I mean, seriously, the algorithm is broken since 10 years, and you have to think about it. Let's compare this to a car manufacturer. Imagine Ford would manufacture cars of which the brakes don't work for 10 years. Would they be liable for it? I don't know. Is the mobile operator liable for having no security? I don't know. Maybe. Maybe not. Okay. Something else that I didn't mention is we talked about the security, and you saw that there is no public cryptography going on. There's no public key exchange happening. It's all static, pre-known secrets. Once it's a key that is stored on your SIM card, and once it's a key that is stored in the mobile operator's database. Now what happens is, if you lose your phone or if you threw away your SIM card, anyone who gets access to your SIM card only for a second can decrypt all conversations that you have done in the past. How does this work? Someone records all the ciphertext that you generate from your phone. Right now he cannot decrypt it, but once he gets access to your SIM card, only for a second, he can decrypt all past recorded conversations. So every time you throw away your SIM card, don't throw it away, put it in a microwave or eat it or something. Okay. I think that was all from my GSM introduction, GSM security. What David will now do, he will explain you how we set about of saving a lot of money and cracking A51 with $1,000 instead of $1 million. Thanks a lot. David.
Forgot to plug in the power here, so I'll do that. The FPGA on my laptop draws a bit of power, so. Okay. Great. Okay, so I'm going to do a quick overview of how the encryption for GSM works. And the GSM specification outlines a few different algorithms that are used for GSM security. And of those, there's A388, which is your authentication algorithm that authenticates you with the base station here. And so basically what happens is it authenticates and makes sure that you're the right user, and then it also generates your session key, which is your KC down here. And I'm not going to go into more detail about this because that's not what this talk is about. But basically, this KC is derived on both sides and is fed into A5. And that's what is used to encrypt your conversation here. So how A5 actually works is, for example, if you're sending something from your phone to the base station, you generate a frame number, which is kind of like a counter, and is like your initialization vector in the system. And that goes and is kind of like part of the key, or your IV for A5, and that's used along with your session key. And this is a stream cipher, and so it starts spitting out a random stream of bits that gets XORed with your plaintext, and that is used to encrypt your conversation. And then on the other side, the base station reproduces the same bits, XORs it with the ciphertext, and gets the plaintext. Pretty typical stream cipher implementation here. And so how A5 actually works is it's three linear feedback shift registers. And first, to basically initialize these registers with your KC, or your temporary session key, and the 22-bit frame number that's generated, is you start clocking your KC into these registers. So like bit 0 of KC gets shifted into here, into there, and then all of these get clocked forward. And then once these bits start hitting these tap registers here, then they start getting XORed with all the other tap registers and get XORed with your input into here. And so things just start getting mixed around in all the registers. And so basically the state gets initialized by the KC, and then you clock in your 22-bit frame number. And so in theory, after these are clocked in, then the state inside of here is entirely dependent on your 64-bit KC and 22-bit frame number, if that makes sense. And so at that point, they start using this majority clocking method, where they look at these three registers in here, and they only clock the ones that agree with the majority. So like if this one up here is 1, this one's 1, and this one's 0, then these two get clocked. If all these are 1, then all of them get clocked. Like if this one's 1, this one's 0, this one's 0, then only these two get clocked. And so it's only the ones that agree with the majority that end up getting clocked forward from that point on. And so they run that for 100 clock cycles. And then the next 114 clock cycles after that, they actually take these bits here, XOR them together, and that's the output that gets XORed with your plaintext, or gets XORed with the ciphertext to decrypt. And so basically, like, the majority clocking here is kind of to make sure that the registers can only get clocked forward. But we'll show a little later on that that there's actually ways to reverse clock this and do it actually fairly well to make this attack work. So as Steve was talking about earlier, a lot of the other attacks out there are kind of academic BS. A lot of them require, like a few minutes of conversation, and in realistic, sort of situations, you talk on your cell phone, you don't really talk to very many people more than a couple minutes, and it seems like lots of people would be interested in listening to phone calls that are under a couple minutes. And then also a lot of these require full plain text for the whole thing as well, and so you have to be listening to them while they're making the call. You have to be predicting traffic, and then there's also other ones that require a lot of storage, a lot of time, and so we tried to make this as easy as possible for anybody to use, and make it actually practical. So this attack uses 3 to 4 frames that you capture. And it turns out that there's actually 4 frames that we know the plaintext for, and so we just use that bit of basically the known key stream out of A5 to perform this attack. And it uses a combination of rainbow table attack, and also reverse clocking and some other methods that we threw in there. So I'll get to it. So yeah, because of the four frames of known plaintext, if you look back here, if we know basically the plain text and what's going across the air, we can derive exactly what's coming out of A5. So we use the sliding window method where we have 114 bits in each frame, and we're just looking for 64-bit cipher streams inside of that. And so we can actually look at 64 bits from offset 0, 64 bits from offset 1, and so on. And so we can actually get 51 64-bit, or 51 64-bit cipher streams out of this. And what we do with that is, since we have 4 frames, we have 204 key streams total. And if you think about A51 as kind of like a standard landman rainbow table, and you think of Okay, so you type in your password in Windows, and that converts to a landman hash. And so if you get the hash, you try to convert back to a password. This is kind of the same sort of thing. We have the internal state of A51 that results in 64 bits of key stream. And so we're using a rainbow table to basically go the other way, just the same way that you would, with the landman hash. And there are a couple differences here. One of the main differences is that this is 64 bits, and the largest landman rainbow table out there is about 41 bits, or 42 bits, something like that. And that's for all the typable characters over, 7 characters length. And so this is actually a huge table. When we were looking at doing 2 to the 64, it's just like a ridiculous size for a rainbow table. So because we have a lot of data points, it turned out that we can actually make this attack work with only using 1/64 of the entire key space, which means we still have to compute 2 to the 58, which actually ends up being 2 to the 59 because of just collisions in the table and such. But that's still a huge number. I don't even know if is that quadrillion or quintillion or, but it's 120,000 times larger than the largest rainbow table. And so the largest rainbow table, I think, took people like over a year to build, and so the same sort of thing would normally take 120,000 years if you're using the same methods. So how do we do this? How can we compute all this stuff? On a single PC, we optimized our core, our software, and we were able to get about 500,000 A51s per second. And at that rate, it would take us about 33,000 years to generate it. And so we ended up looking into FPGAs. Steve brought myself on, and we managed to team up with some different people. And I implemented this on some of my hardware, which is 68 Pico E16 FPGAs. And this is actually one of them in my laptop. And currently our system does about 72 billion A51s per second, which means we'll be able to generate the whole table in about 3 months. And we're also working on building some new hardware to speed this up, make it cheaper, make it more optimal for what we're doing. So, yeah, that's the card that I showed you just now. And this is our system that has 68 of them in there. And we have all these backplanes. Each one of these backplanes has 7 of these cards in it. So with our rainbow table, where we're reversing the key stream output to the internal state of A51, it's going to end up generating 2 terabytes of rainbow tables. And for our cheap attack that we've outlined, if you happen to have 6 350 gig hard drives and 1 FPGA or a botnet, like if you happen to be one of the Stormworm guys or something, you can crack a conversation in about 30 minutes. And we're also working on an optimal attack that we're going to turn into a commercial product that takes all flash drives, all solid-state disks, and 32 FPGAs, and it'll crack a conversation in about 30 seconds. And then you can also increase your FPGAs to decrease the amount of time up to a certain point. It's really a factor of the speed of the hard drives and how many FPGAs you have. So you can scale it up from there. So now that we actually have the internal state of A51, we only really have it for 1/64 of all of our data points. And so only really 3 out of the 204 will be valid internal states inside of A51. So what do we do now? We load up the A51 internal state into the registers, and then we can actually reverse clock it back. And there's lots of different sorts of things that you can use to check to see if your clocking is valid. Like because of the majority clocking, it'll end up being there'll end up being multiple possibilities for when you're clocking backwards, and because of the tap registers and how things feed back and stuff, you can weed out a lot of the possibilities. But still, at the end, once you clock it back to the key, you'll end up with multiple possible states. And the nice thing is that because we have three different internal A51 states, we just match all of the different possibilities, find the ones that are common between the 3 data points, and those are actually our valid A5 states right after the key is mixed in. And if you have the state of A51 right after the key is mixed in, then you can mix in any frame number, generate the ciphertext, and so it's essentially the same thing as having the key. The only difference is is that you don't really have the key, you just have the stuff that will generate whatever you want. There are ways to solve the key based on this, but it's not really necessary, and so we haven't really looked at that too much. So I'll do a quick demo of like the speed that we're getting with generating the rainbow tables, and also Steve can do a demo on basically how we resolve the stuff out of the tables. And then we'll follow up with some conclusions and questions. So let's see here. Oops. Okay, so this is running on my machine, and this is actually generating our chains. And so you should see some chains show up here in a minute. Yeah, here we go. Oops. So it's actually going pretty slow here. I'll just put these side by side. And so this window down here is actually running on the FPGA in my laptop here. And it's quite a bit faster. It's about 6,000 times faster than the window up here that's just running on my PC, by the way. But yeah, so we basically do all of our table generation on the FPGAs, and it's actually quite fast. So I don't know. Do you want to demo the other stuff, Steve, or should we do conclusions first? Okay. All right. Let's do this real quick.
So, there's some, okay, whoever used rainbow tables or rainbow table attacks, who knows this? Okay, fantastic, a couple of people. When we generate these huge tables, at some point we have to look up the data. And I'll show you on some of the tables that we generated that I have with me on my laptop. Unfortunately, my laptop doesn't have 2 terabytes of storage, so I only copied a couple. I'll show you how we look up the data if I get my laptop running. Oh yeah, we mentioned earlier that it will take us, that we have 2 different versions. We have the public version that we are going to release, including the tables, which enables you to crack a GSM conversation within 30 minutes or maybe an hour. And then also we have the hopefully commercial version, which enables you to crack it within 30 seconds. And now this doesn't mean that you cannot crack 10 seconds conversation. It's only the cracking time that takes longer. So if someone makes a 10 seconds conversation, then we are recording the ciphertext. We transfer this ciphertext to the cracking machine, and after an hour you get the results and can listen to this 10 seconds phone conversation. Okay, so there's no limitation on the duration of the phone call. We can.
And then you can also listen up to 16 more phone calls from then, depending on the operator and when they recycle their session keys.
Right, because they're reusing their session keys for over 16 times. There are other 16 calls, you get them for free, you don't have to crack again. So let's see if we can make this. Say again? And SMS as well, yeah. So SMS are encrypted with the same key, same as your voice calls. Oh, I should put this onto your main screen. Mm-hmm.
Does the SMS message count as a call, one of the 16?
Say again?
Does the SMS message count as one of the 16?
Yeah, the SMS message count of one of the 16. So you can, after you once derive the KC value, the secret key, you can listen to 16 voice or SMS transmissions. So what we're doing now. Oh yeah, and also we are attacking the GSM A51 state, which is 64 bits, and I'm not aware of any other single person who ever created a rainbow table over 64 bits, or anyone else who managed to crack a 64-bit cipher without investing a lot of money. Okay, let's see what we have. Oh, there's a little bit at the bottom there, but I scroll it up. So David said earlier that we have 204 states that we can use in the attack. And I have just 9 example states here, just as an example. And because it would take too long on my normal computer to process them all. And with these example states, what we want to do is, for all these example states, over all tables that we generated, we want to find the endpoint where the chain stops. And I'm showing this now. So I'm using table 100 to 100. I only have one table with me, and I'm using the start points from the file that I just showed you, which are 9 different start points. And my computer now very slowly is generating the endpoint. So when we hit the end of a chain, where we use a distinguish point. Yeah, if you're interested in details, you can read on our webpage. Now, with these distinguish points, we want to look up the chain number, the start of the chain. So once we have the start of the chain again, we can start there again and use the A51 encryption and see when it hits our state again, because then we have derived a state that generates the key stream that we were looking for. And we are trying to do this now. We are looking up the data in one of our tables. Again, only table 100. Oops, did I type the right thing there? Oh, that's not right. I should filter this. We're only interested in the ones that actually exist in the table. So we saw for a couple of states that we had from the 204 states, we calculated them further down until we had a distinguish point. And from the distinguish point, we want to find out where the chain starts. And we have a couple of hits here. We see, the endpoint, whatever starts at chain number 794260A, for example, or the other ones. I'm just using the third one from the bottom at the now for testing. What I do now, I take this chain number and I start from the start of the chain to calculate down until we generate the output that we were looking for. And that is 794260A, and it's table 100. And oh yeah, no, sorry, sorry for this. Let me show you the start points where we came from again. And the third one from the bottom here is D9, E9, F, whatever. And we now basically want to find an A5 state that generates D9, E9 as an output in the stream. And the rainbow table helped us to tell us the chain number where we will find this key state. So we're trying to find it again. Minus L minus S, and that was OX79426DA. And we are looking for state D9, E9, FDDC 6F223489. Haha, not found. Okay, let's see. What did I do wrong? Do I have a typo in there? Yes, that would make sense. Let's try this with 6. Also not found. I must have another typo. D9, E9, F, DDC 6F223467. No, it's 7. 7960. Well, let me take a look at this. Say again? Oh no, I see what it is. I forgot the table number. Okay, I forgot the table number. We are here operating on table 999, but I only have table 100 with me. So now when we operate on table 100, we see that in chain number 0794 whatever, when we start from the top, we actually have a state that when we use an A51 will generate the key stream that was used in the original GSM transmission. So this is how we do the lookup. Right now it's a little bit scripting and typing, but yeah, we are planning on automating this a little bit, makes it a bit faster. Okay, that was the demo, and I give it back to David to explain a little bit more.
Jesus. Yeah, sure. Do you want to stay up for the conclusion stuff?
Yes.
Okay, so yeah, we're currently working on the tables. We're about halfway through right now. The rest of them will be finished in March, and yeah, we're coming out with a commercial version. Also, the stuff that he demoed, it was just running like in software on his machine, and so we have part of the core is working for doing all of that on the FPGA, and part of the attack is with this is that normally when you look at Landman rainbow tables, you have like maybe 6 gigs for your rainbow table. And you're wondering how like something 120,000 times bigger only takes up 2 terabytes. Part of that is because we offload the real-time phase onto the FPGAs, and that's really the only reason why we're able to do this. And yeah, you'd probably need thousands of machines in order to actually do this on your PC, actually looking up through the tables or an FPGA. So we plan to make this scalable to whatever decryption time period you have. So if you want to crack something in a couple seconds, it's all linear based on money. So if you have money, you can crack stuff really quickly. Go ahead.
Yeah, just a summary, the cheapest device you could get away with and you want to crack within 30 minutes would cost you would require 1 FPGA, which you get for around $300, and you require 2 terabyte hard drives, which you get for $500. So you're roughly around $1,000 for the entire setup. And it will take you 30 minutes to 60 minutes. If then every time you halve the time you want to crack, you have to double the money. So if you add 30 seconds, it gets a little bit more expensive. But yeah, that's roughly that.
So actually, these are kind of your slides.
Oh. Yeah, okay, let's talk about threats in future. And what did we learn today? First, we learned GSM is not secure. And we know GSM has to become secure because it is a big network. And anyone who has a mobile phone has access to any other mobile phone in the world just by addressing with a phone number. Or this is basically a network plug. We know it will increase data and identity theft. We know tracking is possible. With the cheapest device, we know where the other people are around us. We know there's unlawful interception going on. And we know that will be happening once the GSM network is open and more people get access to these devices, how to access the network, and they get cheaper and cheaper. People will start playing around with the GSM infrastructure, so they start brute forcing, overflows, whatever's there. The software is written from the 80s on there, so go figure. Yeah, receiving and cracking GSM will become cheaper, and it will be a good future. Thank you.
Yeah, so now we can take some questions.
Yeah, the current analysis is based on the GSM standard of games. As you look forward to what you want to does LTE have the same standards or have this role in there that make your life more difficult?
I didn't completely understand the question, but maybe I got it. Okay, we are looking, obviously there's UMTS is being rolled out, and there's a proposal for a better encryption algorithm, Kazumi, but they already found weaknesses in there. And then again, if you use Kazumi on a GSM network, it still uses a 64-bit key. It only uses a 128-bit key if you actually use it on a real UMTS network. And so the downgrade attack will be valuable for many years to come. I think for at least 5 to 10 years before all phones are purely on UMTS. Did this answer your question? Okay. Any other questions, please? Yes, please.
Do you foresee law enforcement
Possibly. We don't know. As you can tell, we are just 2 tech guys. We didn't do any market research. Okay, anyone else? Questions, please. Yes. The $1 million commercial unit also cracks within 30 seconds. So this was basically our baseline when we wanted to build a commercial solution. We want to be at least as good as they are. Say again? You mean the cost for our device? No, for the commercial device will roughly be 10 to 20% of the current available. So it will be 100,000, 200,000 US dollar, roughly in that area. Yeah. Well, to CDMA, we tried to look into it, but first, getting the specifications is very hard, and the only thing that we know, it's all proprietary. No, we don't know. We don't know, but it does make us feel good. Say again?
So if I have like a data plan on my phone and I'm constantly syncing data with like an Outlook server and Exchange server, is that
No, it doesn't make a difference. There's actually a different key used for internet traffic and voice and SMS traffic. So voice and SMS are using one set of keys, and internet traffic is using different kind of keys. So they're independent to each other. Anyone else? What we do with our phones? We don't use the phone. This rainbow table that we are releasing will be for voice traffic and for SMS. Yeah. For internet traffic? No. No. Anyone else? Questions? Obviously, everything is available on our website. It's a wiki. You can add information. You can subscribe to the mailing list. We keep you updated. Well, then, thanks a lot. Oh, yes, sorry. There's one question. Okay, there were a couple of things I was shocked. First, I was shocked when I saw that there's an IMSI on the network just floating around, and the specification says it shouldn't be on there. And then I was surprised how fast we could implement A51 on the FPGAs, because as David says, 120,000 times faster than a normal PC. And yeah, it's just incredible speed that is available to anyone these days, which is cool. All right, thanks a lot. Oh, no, another question. Yes, please.
Back on the putting JVM on a SIM card, and so I had it for a second. So what if you have access to the card for whatever reason temporarily in your SIM? But if you need to do the cracking afterwards, once you get the LPCs, the previous, can you forward cracking without having to generate LPC?
Yeah, the question was what I mentioned earlier. If you throw away your SIM and any attacker gets access to your SIM, he can decrypt your recorded. He can decrypt the traffic that he recorded previously, but that he wasn't able to crack previously because he didn't have the key. Now, what the attacker does, he takes your SIM card, he puts them in a normal SIM card reader, connects to your PC, and there's an AT command, which is called a run GSM algorithm, and he feeds in the random number that is sent in clear text from the base station, and the SIM card returns you the KC that was used for this session. So you can very quickly generate all the KCs that were used during the session, and then crack the recorded sessions, and then give. I mean, you only need really 10 seconds or 1 second access to the SIM, then you give the SIM back to the original victim, and then you can just decrypt everything.
So if it's not going, like you keep my BlackBerry or whatever, or I'm out sleeping, whatever, and it's my phone, can you crack all forward conversations once it's back in?
No, I cannot crack all forward conversation, only past recorded conversation, because I have to know the rand, unless I use a SIM toolkit and I install nasty applications on your thing for listening to your and stuff.
Or if you can pull off the KI somehow.
Yeah, or if you can pull off the KI, but this is not. Yeah, you could, but it's not easy. Past conversation is easy. Future conversations, you have to invest $1,000. Yes, please.
You said that the same session key is used a lot, 16 times, I think you said.
Yeah.
If you turn off your phone before you can make a recording call and turn it on, does that generate a new session key?
Maybe. There's no rule for this. So what we have seen, there are actually networks that generate a new session key for every phone call, for every SMS that you send, which is good. But then there are networks that don't do this. Or sometimes if you roam from one city to another, the behavior is completely different. And yeah, I have no idea if there's a guarantee that when you turn on off your phone that you get a new session key. Maybe.
So have you developed any tools that run on some of the phone platforms, basically to snip to say, to restore the information that you're not getting? For example, is it a new session key every time you change it? Is it encrypted the SMS? How about some toolkits that we could install on some of our phones? Give us that information.
Yeah, we have listed 2 applications on our website which you can install on Nokia Symbian phones. And they will tell you the KC value that you're using and also other information, which channel you're using, which cell you're using, how far you're away from the cell. So you see all this information. Please.
Have you looked at Cryptophone, the open source voice encryption setup?
Yes, of course. Cryptophone.
The RD on the GSM handset?
Yeah, I mean, Cryptophone is not using the A51 encryption, so you couldn't decrypt their traffic. Yeah.
The generation of the E51 has not worked. So the operator decides, instead of reading 16 times, turn it down to 1 time.
Yeah, the operator can do this, but we can also crack this. I mean, our attack doesn't rely. I was living in a network where there was a session key used for every new session. So I didn't even know about this until I traveled outside my city, and I thought, oh, cool, the session keys reuse all the time. So the entire design of our cracker works on the fact that you get a new session key every session, and we can still crack it. Yeah.
What is the challenge that the PlayStation sends to the mobile unit?
The challenge, I believe, is 128-bit for authentication, and it's sent back 4-byte 32-bit. So the answer is 32-bit.
32-bit, so and KC is a function of this challenge and KI, right?
The KC is derived from the KI, which is 128-bit, and from the RAND, which is also 128-bit. And from that they derive a 64-bit KC, unless you have a SIM where the last 10 bits are set to zeros, and you have 54 bits of KC. Yeah. Anyone else? All right. Yes, we will be. If anyone has questions, meet us next door. Thanks a lot.